Okay, so thank you very much for the invitation. So I will speak about Abel's problem over number fields and related congruences. This is a work in progress with Tanguy Rivoal. And first, I want to start with some motivation. So these are Gauss predictions. About the algebraicity of some power series, a construct from hypergeometric series. So we already seen the generalized hypergeometric series in several talks, but I give the definition there. Okay. Oh, I don't know if it's better. It's motivation. Okay. So this is the original motivation of this work. We found this prediction in a paper of Zagier, and we try to solve it. So you start with a rational parameter. And, you just avoid negative integers there. And you construct something that I will write f alpha beta. Not conventional, but I prefer to write it like this. And you have the alphas as numerators and the betas and here this stands for the Pochhammer symbol, which is this. Okay. So these are generalized hypergeometric series. Some example. Really simple one. You just take one parameter at the top and a one at the bottom, and then you have an algebraic series, which is this one. So it is algebraic. Another example that we've seen in Javi talk is f of 1/2, 1/2, 1, 1. And then you get 2 over pi and this integral. One minus t square, 1 minus x t square. And this is transcendental. Okay, so a last example. So I don't give the choices of the alphas and betas, but if you take a suitable choice of alpha and beta, also of a suitable constant C rational, then you have this choice due to Rodriguez-Villegas, which proves that it is algebraic, and you have these things. So f alpha beta Cx is something that you can rewrite as factorial ratio, and it is this factorial ratio. Which occurs in the proof of Chebyshev of bounds for the repartition of prime numbers. Okay, and so Rodriguez-Villegas proved that it's algebraic and of degree quite big and things. So generally, you have a way to decide whether an hypergeometric series is algebraic or transcendental. This is due to Buckers and Ekman when the differential operator is irreducible. And you have also generalization by Jurkevich and Forsnin in the general case, okay, which gives you a nice combinatorial criterion of interlacing between the alpha and beta to decide whether it is algebraic or not. Okay, so I will define hypergeometric series that are factorial, so that you can find a constant C, so that in fact your Taylor coefficient can be written as factorial ratio. So I will say this, that this hypergeometric series is factorial if you can find a non-zero rational numbers together with positive integers. So that f alpha beta cx reads a ratio of factorial. Okay. So in fact, you have an easy combinatorial criterion to decide whether f is factorial or not. And this is something about the symmetry in the parameters alpha and beta. And you can state it like this. You want that this rational fraction is Galois stable, so that it belongs to Qx. Okay, so an example, for example, yeah, so I make a short break. What? Sorry? F? Ah, okay, sorry. So in fact, you can rescale this one, and if you put 16. Okay. So you obtain that this is 2n square. Yeah. So this one is factorial. Okay. Okay. So Golychev made the following prediction using the theory of motives. Is that if, so I take this notation with eta because we will see eta in many occasions in this talk. So if you assume that you have a series time x, which is, so it's a Laurent series, which is an algebraic factorial hypergeometric function. Okay, so it is of the form f alpha beta, but you know both that it is factorial and algebraic. Okay, so for example, in this case, eta is Laurent because you have hypergeometric series start with 1. This case, just because you start with 1 over x, yeah. With 1. but there is this x. Not really a big thing, but we will understand why in the. I did not find a clever way to write it. Okay, so you look at this equation that we will consider several times, and we are interested when this has a non-zero algebraic solution. Okay, and this is that I will call Abel's problem. We will see why. Then, so in this case, Golitchev predicted that it is always the case that this thing is has a non-zero algebraic solution, and in fact, we have even more, that this non-zero algebraic solution belongs to the field generated by x and eta. Okay, so another way to say this is that, in fact, exponential of f alpha beta over x belongs to q x f alpha beta. Okay, so you take you integrate this, and the full prediction is that in fact you belong again to this field. Okay, so the aim of this talk is to explain a way how we prove with the real that in fact the prediction is sharp, is that if you take x eta x an algebraic hypergeometric function, then you have the equivalence that this equation has a non-zero algebraic solution if and only if the hypergeometric series is factorial. But we did not prove this, okay, that in fact it belongs to this field and it is still open. Oui. The stressful part of the talk. No? Ah, sorry, but okay. You can still, no? What is your question? Yeah? About the symmetry on alpha and beta? No? Yeah? Factorial means that you can rescale the hypergeometric series so that you can write it as a generating series of factorial ratio. And it is equivalent. Yeah. Negative power. Yeah. It's also known, we say that it is defined over Q. It's the same thing. So a bit of context on this problem. So if you start with a linear differential equation, where you have the usual derivatives. The I are rational fraction, and K is the number field. Then you have something which is called the Riccati equation, associated with L. So you know that it exists, in fact, a nonlinear differential equation. Say Ru is 0 of order n-1. So that you have the following. The Y is non-zero solution of Ly is 0 if and only if U, which is the logarithmic derivative of Y, is solution of Ru equal to 0. Okay, and now we are interested in when does this operator define an equation which has the full basis of algebraic solution. Okay, so you have the following, that if your operator is irreducible, then this equation has a full basis of algebraic solution. If and only if your Riccati equation has an algebraic solution, which I call eta, such that eta is the logarithmic derivative of an algebraic function. Okay, or if you look at this equation, it has a non-zero algebraic solution. Okay. So you see that there is a way to separate in some steps this question. Okay, you have the irreducibility of L first, then you have to look at solution of the Riccati equation, and then if you have one, you are looking at if this equation with a solution of the Riccati has an algebraic solution. Okay, and this was already known by Boulanger and Penlevé. And they coined this problem, which was a question of Abel. So where's the name of the problem come from? Okay. So you take L, and then you have a way to construct R, which is what is called the Riccati equation associated with L. So you start with L, you construct this. Now you look at the solution. Okay. So if we have this question, which is when does Ly has a full basis of algebraic solution, you have an answer in 3 steps. Okay, and each steps can be solved in a finite number of steps. So what I want to say here is that you take an explicit L. So say you have the coefficient, okay, explicit. Then you have an algorithmic way to answer the following thing. So the first thing was a reduction of the problem to the reducible case. And this reduction was done by Singer. Then, when you are in the case of L irreducible, you look at the Riccati equation and you search for algebraic solution, and you have to answer this question. And again, it has you have a way to answer the question in infinite number of states, and it's again in this paper of Singer. And then when you have eta, you're faced to Abel's problem. Okay, so does y prime equal eta y as a non-zero algebraic solution? And now you have a procedure by Rich and another one independently by Baldassari Dwork that we will briefly outline later. Okay. Yeah, Igor. Okay. So now we will focus just on the third question and on Abel's problem. And the first observation is of an analytic type, and it is the Newton-Puiseux theorem. Is that if you have y which is algebraic and a point in P1, then y has a convergent Puiseux expansion at delta in a slit disk centered at delta, and it is like this. So this is if delta is finite, and if delta is infinite, you have this. And here you have complex numbers as coefficients. You have R, which is an integer, and D, a positive integer. And also you have a unicity of this expansion. So if you start with eta an algebraic function, and you look at the equation y prime is equal to eta y, and you ask whether you have an algebraic solution or not, if you assume that you have an algebraic solution, you apply this expansion, and the fact that then eta is y prime over y, okay? And you obtain, for example, at delta equals 0, that eta is the particular Puiseux expansion of this form. Okay, so this is a specific expansion. Okay, so in fact, just this observation is sufficient to cover the rational case. So if you now look at the case where eta is rational, I make a Q bar, but just because in the following it will be more arithmetic. Then, if eta is y prime over y with y algebraic, okay, then if you apply the Newton-Puiseux theorem in each point to y prime over y, then in fact you obtain that eta of x is the sum of things like this, with the alpha I and beta i's are complex numbers. Okay, but then if you have this, you can easily integrate the equation, and you obtain that, in fact, y is the product of the x minus alpha to the beta, and then you again apply the Newton-Puiseux theorem in each delta, maybe not infinite, but okay, and you obtain that all the beta are rational, and this is clearly sufficient. If you have the beta irrational, then in fact you have an algebraic solution. Okay, so this is CNS. Okay, and what is interesting there is that we see that in this case, y is not a priori in the field generated by x and eta, and that in fact you have a power of y which is belong to this, and in this case m will be the PPCM of the denominators of the beta i's. Okay, so the prediction of Golychev said that in the hypergeometric case, m is always equal to 1, seems already a bit stronger, because just in this case you have is clearly not 1. Okay. So then you have an algebraic characterization of the problem, which give rise to the algorithm by Risch and Baldassari work. And this is the following, that so you start with eta algebraic, and y a non-zero solution of this. Then y is algebraic over k of x, if and only if you can find positive integers m such that m times eta is a logarithmic derivative of an element of the field generated by x and eta. So how do you prove this? So this is easy, okay? Just because you will take y equals c nu over 1 over m. and this is more tricky. But the key idea is just that you take P of X, Y minimal, or Y minimal polynomial equation for Y, but you take it over K of X eta. Okay, so coefficient of P are in this field. And then you differentiate P of Y, okay, which is also 0 because P of Y is 0. And when you differentiate it, you use the fact that Y prime is eta Y in the equation. And then you will find a new equation. And by minimality, you finally manage to find a relation like this for eta. Okay? And in fact, you have more. When doing these things, you can find the shape of the minimal equation, which is just y to the m, which is equal to an element of the field kx. It gives natural breaks. Okay. So in fact, you can find an equation like this. Okay. Where m is m in the characterization, okay? And you find that y is in this field if and only if m equals 1, okay? And so, which correspond to the prediction, okay? The Baldassari work algorithm is to determine in a finite number of steps whether m exists or not by geometric consideration on the curve associated with eta. Okay. The problem is that it is so adapted to if you have one equation which is quite explicit, but if you want to solve something with parameter, especially if you want a theorem on hypergeometric series with parameters which are unspecified, so it is not really efficient, or at least we did not find a way to apply this. And the idea was more to look at an arithmetic characterization of the problem, and to use maybe so theorem of the Chinowskis. which is, so you start with eta algebraic over, say, kx, where k is the number field. Okay. Then we have this. So y prime equal eta y as a non-zero algebraic solution. It is, in fact, equivalent to, so if you have this, we already seen that with the Puiseux expansion, you can prove that, in fact, eta starts with a coefficient over x, and we say that it starts with 0 over x plus other terms, okay? And then you have these S0 have to be rational numbers, and exponential of this primitive belongs to these things. So it is a weak form of the Grothendieck-Cast conjecture because, so this thing stands for the localization at a finite number of primes. So here, k is the number field, OK is the ring of its integers, and you just avoid finitely many prime, okay? So this is the same if we take something like, in the rational case, think like this. Okay? Then you have the real property, which is that for almost all primes p, the p curvature vanish. Okay. So in fact, from 1 to 2, this is Eisenstein theorem. Because if you know that y is algebraic, y is mostly this, and in fact, by Eisenstein theorem, this is an periodic integer for almost all p. Okay. Then this we will see later. This is algebra. Okay. And this is the real difficulty of the Szymanowskis. So the idea was to reformulate this in terms of congruences for the coefficients of eta. Then you have the same one, okay? And you want to traduce it as congruences. So the fact that this is almost a sequence of a generating series of integers, it will be equivalent to the fact that it has what we will see soon, Gauss congruences for almost all p. Okay, and so first, when we look at the prediction of Golychev, we prove this equivalence, but over Q. And our first idea was to look at the paper. In fact, first we look at the theorem of André about when does a G function and its inverse is also a G function. But then we relied more on this. And finally, we use some things which is called the lemma of Dieudonné and Dwork to go from 2 to 2C. Okay? So this is classical. And it is a lemma of Dieudonné and Dwork I will recall. And what I want to emphasize on is that it is a result about integrality. Okay, with K number field. network is in fact in the maximal unramified extension of Q. And if you specialize to number fields, you have I will write it down. This is the part of in progress where we work on number field because at first we were assuming that eta has the rational Puiseux expansion, that at some point you can expand eta and that it has only rational coefficient, but it was a bit artificial. So, okay. The third thing is so these things was proved by Boston, the traduction of the vanishing of the p curvature in these settings, give rise to something that I will like to call Cartier congruences. I will explain why later. At the moment, it has they are not really named, but I will explain later. So, and here we will see that the key idea is a formula, in fact, for the p curvature for order 1 equation, which goes back to Jacobson. Even if it's paper, it's not really clear to see the precise formula. And I just lost the year. Okay. For later. Okay, so what are these congruences? So Gauss congruences. So Gauss congruences, you start with a sequence with algebraic numbers, okay? And you take a prime which is unramified. So if you're not familiar with this, you can just stack at Q, okay? And you can forget unramified. And then we have for every n and every s non-negative, a of n p to the s plus 1 minus tau of a of n p to the s belongs to ps plus 1 and in the localization of OK at p. Okay, so just numbers. And here, tau p is an element of the Galois group of k over q, which is the Frobenius, associated with p. So again, if you look at the initial case, k is equal to q, you can just take T is the identity, and P is just the prime generated by P in Z. Okay. So what we see is that these are congruences that hold for higher power of P, P square, P3, etc. And this is typically the type of congruences that occur in integrality results. Okay, but if you take the ground step of Gauss congruences and you just look at S equal to 0, now you have what I would like to call Cartier congruences. So same things, but just A of NP minus tau P of A of N is congruent to P is in P, okay, P. The thing that we encounter in many papers, this kind of congruences, but with tau is identity, and we have not practical name to name them. And in my opinion, we have Gauss congruences, which are higher congruences, and Cartier congruences. Gauss congruences talks about integrality, and it is in fact integrality of the Artin-Mazur zeta function, exponential of things like this. Okay. And it is an equivalence, okay? Yeah, thank you. Thank you. And the first step of the congruences, in fact, you can, if you look at the Cartier operator that used Fritz in his talk, which we can look at this. It is a Cartier operator that sends sum of an xn to sum of A and P. You have to take this xn, and it's you can define it on perfect field F, say Fp, and in fact you see that satisfying these congruences is exactly for the generating series to be fixed by the Cartier operator. So it's why I would like to put this name. Okay, and in the same spirit, we also encounter in the workshop Dwork congruences and Lucas congruences. And in fact, Dwork congruences are something which is about integrality, and it is integrality of the mirror map, something like, I never remember, G over F of F over G, G over F. Thank you. So, and again, beyond this, you have the lemma of Dieudonné and Dwork, and again, there are huge congruences to write down, and modulo P to the S for all S, okay? If you take the ground level of Dwork congruences, S equal to 0, you have what is called Lucas congruences that we saw in the talk of Fritz. And in fact, this gives rise to structural results about algebraic independence of series. The same thing for Cartier, which gives algebraicity due to the theorem of the Chinosky of the solution there. Okay. Alice's paper said that yes, he proves the equivalence with Gauss, Cartier, and all of things over Q. And here we just extend it to a number fields. Gauss 0, yeah, 1 or 0 as depending, yeah. Like Lucas and Dwork, same thing. So in this particular framework, they are equivalent for almost all P. That's the funny part, that just because it occurs for almost all P, that they become equivalent. In fact, beyond this, you have the fact that the vanishing of the P curvature is a statement mode P, but in fact, it already gives information mode P, higher power of P. And I think it is the same thing, that if you know that you have Cartier congruences, in fact, it leads. Sorry. Yeah, if they hold for almost all P. Yeah. K is Galois, I forget it, maybe. Sorry? If you have a number field, you have finitely many primes that are Ramiched, and then you can forget them and just look at Ramiched primes. It's why the statement for almost all, in fact, avoid Ramiched. And I did not want to take risk to define Gauss congruences for Ramiched primes, even if I have a guess, because we don't need it. So I prefer to wait that it become used. Okay. So there is a funny lemma. the same as one of the Szymanowski. So you start with eta algebraic. So say we shall say this. Yeah, maybe this is missing. I assume it was always Laurent series. So Laurent series, we focus at 0 for the moment. So when I say that it has congruences for the generating series of the AN, okay? And it is at 0, okay? In fact, so you can put eta in, it has a coefficient in a Galois extension of Q, okay? So that this is well defined because you want to bring this Frobenius. Okay? If it has a non-zero algebraic solution, then for almost all P you have this, and for almost all P you have this. In fact, this is just the same thing that the vanishing of the P curvature gives Cartier congruences. We will see it. It's not that difficult. It's linked to the Jacobson formula. Just before this little lemma, which is quite funny, is that in fact, if you start with a Laurent series, which is algebraic, so you can assume that it has a coefficient algebraic, but in fact, since it is an algebraic function, it is definite. So the coefficient lie in a number field, and you can always embed it in a Galois number field, and everything is well defined. Okay. If this has Cartier congruences for almost all P, okay, then in fact you're obliged to be of the form Q plus X kx. It's just fun. Just these congruences give you this, and beyond this, you have Chebotarev result, because in fact you have that A0 is always congruent to A0 mod P for almost all P. And it gives you that A0 is in Q, which already detects the equation, this one, which has no algebraic solution. And we see this just with congruences because we are not in Q. It's just... Sorry? Yes, thank you. Okay, a corollary is that, in fact, if you write this eta algebraic, and for delta a point in Q bar, I will set eta delta is just x minus delta times eta of x, okay? And at infinity, just x eta of x, okay? Then you have a way to rewrite things at other point, because in this statement we focus at the expansion at 0, and we assume that it is Laurent. So you have no singularity at 0 of the algebraic function, and you have, but you have no the Puiseux expansion is with d equal 1. Okay, it's a Laurent series, it's not in full generality. So you want eventually to look at other points. And what is fun is that since the condition 1 is global, it doesn't look at a point where you expand your function. In fact, you can see that you have that n delta 1 as Gauss or Cartier is the same, Cartier congruence for almost all P. What I mean by this is that you extend, you look at the expansion at delta 1 of this function, okay? So you have new coefficient, and it is equivalent to n delta 2. What you do is that, for example, at in a finite point, n delta 1, you will write this. Like like this. You expand it as a Puiseux expansion at delta 1. You have coefficients there. Since delta 1 is algebraic, you have the AN, which is also algebraic. And you have this. So the congruences are not dependent of the point where you look at it. Okay. So now I would like to briefly explain the tools beyond the traduction in terms of congruences. So when you look at 2 from 2c, so the integrality of this exponential, and you go to the Gauss congruences, the tool is the lemma, which is really classical, of Dieudonné of Dwork, and that you always use when you look at integrality of exponential. So, Galois. So we state it in the setting of algebraic number theory, P and Ramiched. So this is at this point. Before it was a bit artificial to just stuck at an Ramiched prime, but at this point you're obliged. The lemma of Dieudonné and Dwork doesn't work because at some point P fights with factorial n, and he can't win if it's Ramiched. Okay, so what you have is this K-Galois field, and so the Frobenius, and you start with a series which has 1 as constant term. Then you have equivalent between f of x as in fact periodic integers. So this is localization at P. And you look at this ratio. So you apply the Frobenius to the coefficient of f. X is raised to the power P. Here is fx power P. And you want that you have 1 P. This is the rational prime there, P. X times OK. So here, okay. So why it is important is that because in fact, as you see, you're looking at integrality of a function, and you trade this for the integrality, maybe more demanding, but of a ratio. Okay, and then it turns out that you can prove that if you start with now a power series without constant term, then the following are equivalent. The exponential of s of x as periodic integer coefficients, if and only if you have this. This is still the rational prime there. And so just the corollary says that this lemma is really adapted to exponential. So what happens is that if you want to prove that this is with integer coefficient, then in fact you have to forget about the exponential and just look at some congruences about the power series there, okay? And you want that the coefficients are divisible by P. Then if you apply this to our situation, you start with eta. No, P fixed. Yeah, P fixed. This is a periodic statement, okay? Yeah. So you fix P, and then you just look at this, and then in fact you will look at this for. In fact, since you want to prove that it has the exponential of this. Is almost an integer power series, so it has an Eisenstein constant in some sense, then in fact you will just try to prove that this holds for almost all P. And the traduction of this, and now you replace S by this, just give it leads to Gauss congruences. It's just a little exercise. The traduction of these things. gives Gauss congruences there. And then you manage to have the equivalence. Okay. Gauss congruences for x eta x. Here I'm talking about, again, the criteria. So I stuck to the case where it is a Lorentz series. But you can easily do the general case from there. Okay. So now I will just talk about so we have the link between 2 and 2c, and now we will look at the link between 3 and 3c, okay? And together with, in fact, the link between 2 and 3. So the fact that if you have something which is almost integral, then the P curvature vanishes. And the thing is to consider this map. So here, Kp stands for the residue field. Okay, so over Q you will have P. And what you do is that you assume that eta is reducible mod P. So since you know that eta is algebraic, you know that it has an existence constant, and that for almost all P, you can reduce it modulo P. Okay? So eta is a Lorentz series. Eta is of this form. Okay, so in fact like this. But, and you will just reduce eta mod P, okay, for almost all P. Then the map here, delta, is defined by delta of y is, you take the first order operator, and it gives you this. So it's well defined because eta belongs to Kpx. Okay. And then you can look at the piece iteration of delta, which gives rise to the P curvature. So you just look at the delta to the P. And the thing is that you have a Leibniz rule on delta, and it's just so all of this was contained in the course of Julien Roch over rational field, and this you can prove also that it is Kp x to the P linear. because it has a Leibniz rule that gives you this. But the magic is that, in fact, when you raise is to the power p, if you make the calculation, you see that, in fact, this is k p of x linear. Okay. Which gives you the following, is that now this map is 0, so the p curvature is 0, if and only if you have a power series solution of delta, so the original operator. And in fact, if and only if delta p of 1 is 0. So why? Because if this vanishes, so it means that delta has a non-trivial kernel, okay? So it has Lorentz series non-zero as a solution. But then since it is x to dp linear, you can multiply by a high power of x to dp to the fact that now your solution becomes a power series. So you have a power series solution from this, okay? So now the point is that for the reverse, if you have a non-zero solution, then you have a non-zero solution of this one, but it is kpx linear, so it vanishes on all of kpx. And now, in particular, it is the same as saying that it vanishes at 1. So why we are interested in this? So it is particular to the order 1 case, because in fact you have a formula by Jacobson. I don't really know if you prove this on Q or Q bar, but I think it is true everywhere. Mod P is really purely algebra with the fact that P is 0 in certain binomial. So you can reprove this, no problem. You have delta P of 1 is minus the P minus 1 derivative of eta minus eta 2 dp mod P. Okay. And so you have this formula, and now you want to traduce this in terms of the coefficient of eta, and you have to work a bit, but you find Cartier congruences. So by the Chinosky, you want this to vanish for almost all p, so you want Cartier congruences for almost all p. Okay. And for the Gauss congruences, you want it to be almost an integer, so you want it to be a periodic integer for almost all p. Why is almost all p everywhere? Okay. So, okay, for all of this, briefly, why we can, why it is useful in the hypergeometric case. For the hypergeometric case, it was already said that the key feature is that, in fact, you have this an plus 1 over an, which is a rational polynomial with coefficient in Q. And in fact, the coefficient of the hypergeometric series are multiplicative. Okay, there is no sum. So for this reason, the congruencies, the periodic valuation, and the study of the arithmetic of hypergeometric series is quite simple, and you have great tools. And in particular, you can easily prove something which is close to the Cartier congruences, and which is almost. So just before, I will take this notation. So and this. Okay, and I will call D the common denominator of the alpha I and beta I. Okay. Then, if you take a prime P which is strictly larger than D, if you take hypergeometric series, which is globally bounded. So I think it was already defined in the talk of Ravier, but just to recall, it has a positive radius of convergence, and I think we have to put the C in front. No, not for this one. You can rescale f so that it has integer coefficient with a non-zero constant. Okay. So, okay. So let's say that we have this. Then you have always these congruences. Maybe I can drop S just to stay simple and look at Cartier. In fact, it's also for Gauss congruences, but you have this. So the hypergeometric term in NP is congruent to another hypergeometric term, K alpha, K beta, in N, and mod P. So here we are in the field of rational numbers. So the point is that if we look at Cartier congruences, we are almost Cartier in the sense of if this is alpha, we win. It is Cartier, okay? And this is beta also, but this is not. And this is precisely the point, is that, so here, just what is K? K is an integer, which is coprime to D, and which is the inverse of P modulo D. And this strange angle is just the fractional part, almost. So if x is not an integer, you take the fractional part, but just you don't want to put the parameter on 0, since it is an hypergeometric series. So you take 1 if it is an integer. Okay? So for example, if you take D equal to 6, P equal to 11, so calculation gives you K equal 5, and then you have the fact that Q 1/3, 1/3, 1, 1 in NP is congruent to Q 2/3, 2/3, 1, 1 in N mod P. Okay. And the point is that with this, in fact, you will prove that you have the Cartier congruences. For almost all P. It will be equivalent. So here you will need the Dirichlet theorem. Because what you will do is that you want that this holds with alpha and beta here, but you have this sequence instead, and now you will take infinitely many prime P, which realize each congruence class of modulo D, and then you will prove that in fact it forces the equality on the parameter. Okay, and doing this, in fact, it is exactly the same as asking f to be factorial. So you obtain your equivalence. Okay, and just I finish in 1 minute. It's just some curiosity that so in some sense, so already we characterize the hypergeometric series that has Cartier congruences, and we have other type of series that has these congruences. The first one is trace of AN, where A is a square matrix with algebraic integer. Okay? So all of this satisfies Cartier congruences for almost all P. Of this, what we already seen, at least in the talk of Francis, is this, and Fritz also, I think, constant term of power of lambda, where lambda is a Laurent polynomial. In several variables. Okay? And another thing, it is a fixed point of an iterate map. Okay? And just F is a map on a set X, but you ask that for such that for every n, the number of fixed points is finite. Okay. So all of them has, so in fact, all of them has even more Gauss congruences. Okay. Maybe this one is, I think, yeah, for an ramified prime here. Okay. And then you have a funny construction, which generalizes this. You take trace of an, but the constant term of this. And with a square matrix, but now of Laurent polynomial. You can prove that it is that it has Cartier congruences. I think that it has Gauss congruences, but I'm not sure. I think that there are diagonal of rational fraction, but I'm not sure. And okay, and I know that it was already studied by Kontsevich and Rotteiner in the free variable case, where they prove that the generating series is always algebraic, also with the exponential of eta. In the free variable case, it is always algebraic, but in the when variables do commute again, in fact, it's more tricky. But since you have this, in any case of this, if you take the generating power series and the exponential of this, so that, by the criterion, they are both algebraic or both transcendental. And I will stop there.